Now, it is again integration theory of Riemann-II. So, and as I told you the story earlier that when Riemann showed this to his supervisor, PhD supervisor, Gustav Dirichlet. Dirichlet is very famous in many parts of mathematics, including partial differential equations and all those things. So, Dirichlet gave him this function which is nowadays is famous as the Dirichlet's function. If x is equal to 1, if x is rational, is equal to 0 if x is irrational. So, let us look at the function, let us look at this function and let us assume that we want to integrate this function from 1 to 0 to 1 fx to dx. It could be any a to b, it does not matter. I am just putting 0 to 1. So, if I want to find this integral, what does that mean? So, again I want to tell you in the Riemann integration theory, if fx is greater than or equal to 0, even if it is a bounded function, need not be continuous, but greater than or equal to 0, then the Riemann integral is, for a non-negative function, the Riemann integral also has another name which is called the area under the curve. So, what is this? So, we take a partition and construct the upper Riemann sum. You see, whatever be your bound, whatever be your partition, does not matter. In every partition there are of course countable rational numbers and uncountably infinite irrational numbers. So, 1 is always the upper bound, 0 is always the lower bound, right. So, basically, so you will have 1, 1, 1, 1, 1. So, basically, if you finally it will be summation 1 into xi minus xi minus 1 I is equal to 1 to n. So, this is if I have n points, maybe you would like to write it as UFPN. But then this, if you add them up, this is nothing but the interval 0 to 1. So, the length is 1. But if you write LFPN, it does not matter whatever be your n, it is always 0. So, you take the limits of these two as I have just showed. So, or if you take, so it does not matter what is your, so whatever be your partition, this is what is the answer. So, UFP is always 1, LFP is 0. So, you take the infimum of the supremum of this and infimum of this is 1, supremum of this is 0. So, I take the inf over all possible partitions and I take sup over all possible partitions. 1 and 0. Okay. Now, so UFP is not, inf of this is not same as sup of LFP. So, if they are not same, the function is not Riemann integrable. According to Darboux rule, this is not Riemann integrable. So, this function is, so this does not exist. So, how are we going to show that Riemann integral exists. So, we are now going to reconstruct the definition slightly and write it in a more workable form into a necessary and sufficient condition. It is slightly important enough that we can call it a theorem. It says that a bounded function f from AB to R is Riemann integrable obviously in the Darboux sense. But Darboux sense and Riemann sense are same. We have not mentioned the theorem that I will mention at the end of this class. So, f is a bounded function and it is Riemann integrable in the Darboux sense, then there exists a partition P, then for any given epsilon, or we can write a more complex statement, if and only if, I was just trying to separate them, if and only if for any given epsilon greater than 0, no matter how small, there exists a partition P such that UFP minus LFP is strictly less than epsilon. Now, let us try to give a proof of this. You will see it is a restatement. If you think of it, it is a restatement of the definition. First, I will assume that given an epsilon greater than 0, I will assume that there exists a partition P for which this is holding, this fact holds. So, in the proof I will start in this following way: given epsilon greater than 0, given any epsilon greater than, given any epsilon greater than 0, there exists, there is a symbol of there exists which mathematicians use, for short I am doing it, there exists a partition P for which U F P minus L F P is less than epsilon, is given to you. So, what I can write that U F P is strictly less than L F P plus epsilon. Okay. Now, infimum of UFP over all possible partitions in the partition set is now less than equal to UFP, right, or maybe I will write as P dash. So, the infimum could be less than or equal to this, right, and this is strictly less than LFP plus epsilon. But what is LFP? It is less than or equal to supremum of LFP double dash or LFP dash, P dash in P plus epsilon. So, if I look at this expression, what I get? So, for any epsilon greater than 0, I have just proved that infimum p dash element of p u f p dash is less than or equal to, sorry, is strictly less than supremum of L f p dash plus epsilon, where p dash is obviously varying over p. So, you have inf of p dash element of p u f p dash minus sup of p dash element of the partition set p L f p strictly less than epsilon. This is what you get. Now, this is true for any epsilon greater than 0. So, I can make the epsilon smaller and smaller and smaller and smaller. So, in the limit I can take this limit to be 0. So, from here I will simply get the result that inf of u f p dash element of p is less than equal to sup L f p dash dash element of p. That is exactly what I will get, because if I just write the limit, this has to be less than this, when this will finally become 0, I can make this to be 0 in the limit. So, when you go to the limit, this breaks, the strict inequality breaks. This whole thing has to be less than or equal to 0 for this has to maintain for every epsilon. Technically, if epsilon is strictly greater than 0, then this quantity actually, because this quantity is always bigger than this quantity should be 0. Obviously, no, you know that already we have studied that this is bigger than this, inf of this is always bigger than this. So, essentially what we get from here is this, and once we get, you know that this common value is nothing but the integral, so the integral exists. And now we will make the reverse proof that, okay, if the integral exists, what happens? If there is an integral, then there is a partition p dash for which this is true. So, now we assume the converse. For the converse, assume that integral a to b fx dx exists. Exists means it has a finite value, which implies that supremum of p dash over p LF p dash is equal to infimum p dash over p u f p dash. So that's what is known to me, right? So I'll now apply the definition of infimum or supremum, and we will get some conclusions. So we'll just apply the definition of an infimum supremum here. Okay, so we have come out to here. This is, if it is integrable, this is what we know from definition. Now, inf of this is actually the supremum of this. So, this is the supremum value of this quantity. So, which means that given any epsilon greater than 0, there exists some partition p dash such that if you subtract from the supremum of LFP some the epsilon by 2 quantity, there must be some partition for which the LFP, that value of the lower sum must be strictly greater. That is the meaning of the supremum, that this is the supremum, nothing else can be the supremum. That is, there cannot be anything which is an upper bound, there cannot be any quantity which is an upper bound as well as less than the supremum, strictly less than the supremum. So, similarly, the sup of this is actually the inf of this. So, there must exist a p star, so that if you increase the value of the lower bound, that is the greatest lower bound, so it cannot be a lower bound. So, there must be some p dash for which u p f dash should be this, because this is at the inf of u p dash. So, basically you can start writing here sup of L f p dash, then which is actually equal to inf of this. You can replace. Now, if you combine these two, you will get this relationship. Now, the last part of the result is very simple. You consider a P, partition P, which is P star union P dash, P double dash, and in this you already know the result. We have done it, that if we take a union, the upper sum reduces, right? The upper sum will reduce. U f p is less than equal to U f p star, and L f p would be bigger than, lower sum increases, L f p double dash. So, if you combine them, then you will have U f p minus L f p is less than or equal to U f p star minus L f p double dash, which is strictly less than epsilon. So, finally we conclude that I have got a partition P, which is the union of these two partitions. We have shown the existence of the partition such that U f p minus L f p is strictly less than epsilon. So, this shows the final conclusion, that conclusion. So, this is an if and only if condition for integrability of a function in the sense of Riemann worked out in the Darboux approach. Now, let us see how useful this result is. So, to show this, we will actually apply it to a problem which I take from Spivak, but it is a standard problem. It can be found in many texts, but it is important to mention the reference that you are working with. So, students should actually know the text which the instructor is looking at. So, I will take a very simple problem. It would look obvious, you will immediately tell me the answer. So, the function is like this. And f(x) is defined as follows, is equal to 1 is equal to 0. Now, so what is, if I draw the graph, it is just like this. So, at the point 1, it is 1. So, below that it is 0. Here is the discontinuity. Okay, now, what will we do? You have to understand this 1 will either be a partition point or it will be within some partition point. It does not matter. So, there will be, suppose I take a partition point, say Ti and 1 is here. So, its upper sum, whatever be the partition, right, the upper sum is UFP is equal to Ti minus 1, assuming that I do the partitions at the I, it is in the ith interval. It could be in some other interval, does not matter. Similarly, the lower sum, it does not matter whatever is your partition, is 0. The lower sum is 0. Now, what is the difference between UFP and LFP? But I can make the partitions in such a way that I can make this Ti minus 1 to be as small as I like. So, given, suppose I choose an epsilon, and I can always choose 2 points Ti such that around the point 1 such that Ti minus 1 is strictly less than epsilon. So, it does not matter whatever epsilon I have, I can always construct a partition P in which the ith interval Ti minus 1 would be strictly less than epsilon, and that would contain the number 1, and so I will immediately get this, and from that theorem I will immediately conclude that f is integrable. Now, what is the value of this? You will immediately say 0, come on, what is the value? See how you do it here. See what is happening here is that if you take the inf of UFP, the inf of UFP is 0, because I can make this as small as I like, bringing I and I minus 1 closer and closer to 1 from both the sides. So, inf of UFP is actually 0, and the sup of LFP is obviously sup of LFP is actually equal to 0. So, hence these two are same, and so integral 0 to 2 fx dx is equal to 0. So, you see it is a very simple way to calculate. Of course, you can say, oh, I can look at it and say the integral area is 0. But here it is a very rigorous approach, that if there is a discontinuity at one point, it does not matter, I can still compute the Riemann integral. So, if a function is bounded and but still has discontinuities at some finite number of points, then it is still Riemann integrable. So, discontinuity at finite number of points can be forgotten. So, for a Riemann integral function, discontinuity at finite number of points is not the issue, right. So, here is a very important lesson to be learned from this very simple example. Now, I will state this result, the Darboux result, which one of the best ways it has been stated is in a book called Principles of Real Analysis by Ali Prentice and Burkinshaw. I will just show you in the camera so that you can, because nowadays people take immediately, you will just take a shot of the book rather than writing it. People do not waste time nowadays, this is evolution actually. Okay. So, what they say, what they prove is the following. They prove that the integral in the Darboux sense and integral in the Riemann sense are same. So, let me just tell you, maybe I should not waste time, I will just write it down. So, integral in the Darboux sense and integral in the Riemann sense are same, that he says that okay, limit of, maybe I should just simply write this, n tends to infinity f xi I xi minus 1 I is equal to 1 to n is same as limit of u UFPN n tends to infinity is equal to limit of n tends to infinity. Of course, the proof is involved, as the proof is not done. That should be really done in a much advanced class for graduate, advanced undergraduate class, or even advanced some graduate class in mathematics. And this is same as the Riemann integral of Darboux. So Riemann's approach, whatever class of functions is possible, you can actually integrate by Darboux's approach, you can integrate by Riemann approach. So Riemann's approach and Darboux's approach to the Riemann integral they are the same thing. So Darboux's approach makes sense because it is much more easier to handle. And let me also tell you that a continuous function, if you take a continuous function, it is a bounded function, and any continuous function is Riemann integrable. But we are not doing the proof because the proof needs some notion called uniform continuity. So these little things would actually be provided in the notes. Now what is uniform continuity? What are the main results? How it is applicable to Riemann integrability. So the whole idea is that we have not used this idea of uniform continuity because that is the only place we are going to use it. So we have not just done it. In the next class we will show that using the Darboux approach it is very simple to prove some rules of the calculus, and we will show that if we have something like this. So you have a bounded function and you have so this is a Riemann integral function, and if I can write it like this, you can prove that capital F is capital F is continuous. And once you prove that, that would lead you to the fundamental theorem of the calculus, which we have already learned for the Newtonian situation, the Newton's approach, but we will learn it for the more general approach. That is, for the more general approach, the fundamental theorem of calculus actually holds. So this is important, and once we finish that, those are the 3 lectures which. So that tomorrow we finish that part. So maybe first part would deal with that. Maybe we will deal the whole thing in one lecture, and if time permits tomorrow, it depends on what's the scenario. Then tomorrow I would tend to give you a more of a entertainment lecture. You can say every course should have an entertainment lecture, I believe. It is on how this idea of Riemann's, this idea of tag partition has been actually generalized, making the partitioning more flexible to integrate functions which are not integrable in the Riemann sense. And actually it is better than the official integral of mathematics, that is Lebesgue integral. But Lebesgue integral is so much, as I told you, is so much embedded in our psyche as mathematicians, we tend to forget that something else could be better. So that is the integral due to a Polish mathematician called Kurzweil and Henstock. Ralph Henstock is a British mathematician. So they invented this simultaneously, independently, that they could actually, we will not prove things there much, we will try to give a definition, show some examples that okay, something which is not Riemann integrable but is integrable in that sense. In fact, some integrals which are not integrable in the sense of Lebesgue, which is the Lebesgue integral, which of course you do not need to know about it, is also integrable in that sense. And so this is something which is, there is only one book written about that class of integrals, is due to Bartley, Robert Bartley, who has a famous book nowadays, Bartley-Shepard. So this Robert Bartley's book, I think Robert Bartley isn't alive anymore. Robert Bartley's book, he says that this is the true modern theory of integration, and it should be more famous, it should be more known. Maybe it is not known today, maybe after 200 years that would be taught in every class. So with this I would end my talk, and I hope that you have enjoyed it.